Good afternoon, everybody. I see the room is packed, so it's time to get started. Welcome to the second series of talks, and we'll start talking about microservices. I'll give a very brief introduction. My name is Marcel Offermans. I'm the director of Luminis Technologies and also a member of the Apache Software Foundation. And Google can tell you the rest. That's my Twitter handle, in case you want to tweet about this stuff. So let's move on with the agenda. And before we actually start talking about microservices, it might be worth spending a little bit of time talking about modular architectures and why we even would want to use those. Then we'll dive into microservices, just trying to define what they are, what characteristics they have, sort of to describe the architectural style. Then I need to do a quick introduction of OSGI. I probably won't make it in 60 seconds, but I promise not to spend too much more time on it. Also a quick introduction to Amdatu, and then we can do some live demoing. And given how the previous demo went, I'm really praying to the demo gods that this one will be better. So we'll see how that goes. At least I have a different laptop, so we'll see. So let's first get started with modular architectures and making a case in general for modularity, because modularity, well, it's nothing new in software and it's nothing new in other engineering disciplines. In fact, if you look at most other disciplines, they have way more advanced modularity than we, partly because they've been around for longer. So they might have more experience building systems, partially also because they have more advanced standardization processes. I mean, if I want to build a bridge or something, everything from the nuts and bolts has been standardized, and you can really just design something and worry about whom you're going to buy the nuts and bolts from later, because, well, they're all sort of the same, at least they have the same dimensions, so that's a big advantage. And even at a larger scale, because modularity is really at different scales, you'll see a lot more standardization and a lot more rigorous modular approaches in other disciplines. So we're starting to get that same thing in software too. Modularity is probably a good thing for a couple of reasons. First of all, because it makes your systems in general more maintainable. More maintainable might mean that it's easier to go into a specific module and go and do a bug fix. But as we've seen in the keynote, for example, there's also a tendency to just say, okay, this was an interesting module at the time, we built it, it served its purpose, we're just going to throw it away and implement it again from scratch with all the experience that we have right now. And maintainability is really important in software because it's quite expensive to build a large system. So you don't want to go and replace it every couple of years just because you cannot maintain the current system anymore. That's usually not a very good reason to go to your boss and ask for $500,000. I just had to rebuild my entire software in this new cool language, and hopefully at the end it will do just about the same that it already did. I don't usually get money for doing that. So maintainability is important. Another thing, and the whole agile movement has probably shown us that as well, is adaptability. When we start building software, well, sometimes we have an idea that we know exactly what we want to build, but usually over time that idea changes. Business might change, they might want to do new things with existing software, technologies might change, so you might have a different approach to solve the problem. But there's many reasons why it's good to be adaptable and go with different requirements and different trends there. And another one, and that's maybe a little bit of a controversial point, again referencing the keynote we just had, is our quest for reuse in software. Somehow we have this notion that it's probably a good idea to reuse what we have if we made it once. And there's a good reason for that, because you probably spend a lot of time thinking about a problem, and if you have it solved, it makes sense to kind of reuse such a solution over and over again until you find a better one. And in our quest for reuse, probably what most people have done, and some still do, and I'm also guilty of that, and maybe it's not even a bad thing in all cases, is just use copy-paste. You have some code, it works, and you want to reuse it in a different program, you just copy-paste it. Has two downsides. Well, the first is obvious. You're making a copy, so maintaining both copies will obviously take more time. You fix a bug in one, won't automatically be fixed in the other. So you have to actually make an effort to do so. So that might be a downside. And the other is slightly more subtle, is that, well, maybe you're copying code and using it in a different program, in a different environment, where it hasn't been designed to use. So it might functionally still work, but it could break because of performance requirements or something like that. So you have to be really careful for that. In a lot of cases, the original author didn't really take into account the use case that you now have when you copied that code. So that's something to look out for. And probably about, I think it's 30 years ago, object-oriented languages started to become more and more popular. And with those languages also came reuse. As long as we are just creating classes, these could easily be reused. At least that's what we were told, and that's why we were all starting to learn C++ at the time. A horrible language, I think, but I'm still using it every now and then. But if we look back now at 30 years, probably object orientation hasn't really brought us much reuse either. Classes tend to be hard to reuse if you take them out of context and place them in a completely different context, because there might be a whole inheritance hierarchy. A class might embed other objects, different classes. So it's kind of hard to rip out a single class and use it in a completely different environment. Besides that, a single class is usually also a relatively small unit of reuse. That might not also always be a bad thing, but you also need something that can be reused at a slightly larger scale. So from object-oriented, now with clouds and virtual machines and containers, come other units of code that we can reuse. And I'll summarize them for now as being components. Slightly bigger than classes. They might be a couple of classes, might be tens of classes together that try to solve only one thing and that have a relatively straightforward interface to the rest of the application. And sort of the analogy with Formula One cars is quite good. You can replace those components on those cars pretty quickly. At a pit stop, they do it in a couple of seconds. They can keep optimizing these components, and they do that for every race, trying to get the most out of them. And these components also serve a very clear purpose, namely generate as much downforce as you can and transfer that to the car. So there's an analogy with that, and component-based techniques in software can help us create something that's more easily reused. And well, microservices is one of the architectures that you can use for that. So moving on to microservices. And probably the first thing I should do, and maybe some of you have already done that, go to Google and try to come up with some kind of definition of microservices. And this is, well, a fairly long sentence, but it kind of describes a lot of important aspects of the architecture. So it's about a suite of independently deployable services, and they have some common characteristics. And these are organized around a couple of things. Some of them are more business concerns, some of them are more technical, but there's a lot of information in this one sentence. So probably makes sense to dive down and investigate a little bit what all these different things mean. And this definition, by the way, comes from Martin Fowler. He has it on his website. And let's move on and look at some of these items. And we'll start with business capabilities. So when you start architecting using microservices, you tend to organize these microservices or these components around business capabilities. And that should be your leading principle when trying to break up an application into different components. It's a little bit different from what you might be used to. I guess a lot of you know the architectural diagrams where we have different layers, one being the user interface at the top, then we have some application logic in the middle, and at the bottom we have some kind of database or data store, and that's usually the basis for architecture. With microservices, you tend to say, no, let's take those together and focus on one business capability and make everything that's needed for that part of this component. So it might be a little bit of UI, a little bit of logic, and maybe also a little bit of database. And what's interesting in this context is that there's a law called Conway's Law, and I'll read it out loud. It says that any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. And if you look at your own company, you might see some parallels. The way the company is organized usually reflects the way you build your software. Do you have separate database and application and front-end teams? Then you usually end up with those components in your architecture as well. The point is that if you want to change that and go to a more microservices architecture, that means you might also have to change the way your organization is structured. And that's important because that's usually not the easiest thing to change. So that's something you should take into account. Another principle is that each component or each microservice owns its own data. So you don't have one big database at the bottom that contains everything, but you have different components that are all managing their own data, and that might all choose a different way of storing that data. So in a lot of cases, you'll end up with some polyglot persistence model, but also take care, don't go crazy with that. Don't choose a different database for every component just because you can and it sounds cool. Be sensible about that. Another thing when designing these components is to take a look at domain-driven design. If you're already using that, then you're probably familiar with the term bounded contexts. And those bounded contexts are usually a good way of defining your components. And finally, something you'll see regarding data is that in a microservice architecture, you usually end up with some kind of transactionless coordination between services, because it's hard to try and coordinate a transaction over all kinds of different components if everything is using different types of databases and data stores that might not even support transactions, plus having those distributed transactions. It's really hard, it might slow your system down. So in a lot of cases, you'll end up with a system that has some kind of eventual consistency and some kind of ability to repair any failures or inconsistencies that might occur at any one point in time. Then more on the organizational side, you tend to organize different teams around the individual products or microservices and make those teams responsible for the entire life cycle of such a component. So the developers don't just develop something and then throw it over the wall to DevOps or to the system administrators, to the cloud, and let somebody else worry about keeping the system up and running. That's actually the responsibility of the same team. It's also a way of bringing your developers a little bit closer to your customers who in the end will be using your software. And as Amazon says it, you build it, you run it. Might not be the most fun thing to do if you have to wake up at 3 at night to restart a server, but it's probably a good way to make sure that that never happens, right? So, and of course, I mean, we can't talk about microservices without zooming in on the actual services, because that's sort of the API to the outside world. That's how the different components talk to each other. And these services should obviously provide a public contract. In most cases, it may also makes sense to somehow version these services, because you might want to evolve them over time. And hopefully that never requires an API change, but in practice sometimes it does. So you need to make sure that you can handle that. And also these services, they usually end up with their own life cycles. The ones that were here for the previous talk about Docker containers and creating all kinds of clusters based on those, you'll know that not all of those start and stop at the same time. So you have a way more dynamic sort of cluster of systems, and you need to be able to keep track of which services are running, which aren't, and sort of respond to that. And as a service is the only thing that is exposed to the outside world, everything below that is just an implementation detail, can't be accessed by anybody else, which means you have a very good level of isolation between the different components. And talking about services might also make sense to briefly zoom into how services can communicate. In these architectures, you usually end up with fairly, as I described them here, dumb pipes. So on the one hand, you have systems where you have very advanced message routing systems that do all kinds of caching and filtering and stuff like that. That's usually not what you tend to use in these architectures. You tend to keep those pipes fairly dumb and simple. It might either be just a REST call, so HTTP, request response, or it might be a very lightweight messaging solution. But usually it's not more than that. And, well, we've been talking about a cluster of machines. That also means it's a decentralized architecture, decoupled by the different service APIs, because everything below that is just an implementation detail. It gives us the freedom to choose the language that's best suited for implementing this. Like I said before, don't go crazy with that. You also have to maintain some of those components. And what you also tend to see is that there's sort of less focus on formal standards. And by that I mean, for example, if you're building in a more traditional Java EE way, you tend to have to use all the APIs that Java EE provides you, because that's what they're in your application server. That's what you probably can use the easiest. And with microservices, because the API is the only thing you share, you can choose technologies to implement each component and be less formal, or whether that's a standard and whether that's going to be supported for a really long time, because you always have the option to just throw it away and implement it in a different way. It's still somewhat of a concern, because you don't want to have to throw stuff away because some kind of API or library or something is deprecated, but you have more freedom with that. So that's definitely something you'll see more in these architectures. And probably not even that specific to microservices, but if you have more smaller components in your application, it becomes more important. You have to automate deployment. You cannot go and manually start deploying stuff because there's too much stuff to deploy. You might want to scale your clusters dynamically, and that becomes unmanageable pretty quickly. So not only do you have to have continuous integration already in your development process, making sure that each module works together with other modules correctly, you also probably want to go to a way of continuous deployment, or at least a very easy way of deploying things. I'm still not sure if it makes sense to continuously deploy new features in an application. I really haven't seen many people doing that. While you're using it every minute, you have a new feature coming in. It's probably going to confuse your users as well. But make the whole process automated so it becomes easier to deploy updates, maybe also to correct mistakes if something goes wrong, that makes sense. And then some general sort of design advice. Well, I mentioned it a couple of times already. It's important to design for change. When doing that, that starts really early, when you start to decompose the system into different components. That's when you first have to start thinking really hard about, okay, so how is my system going to evolve? Because that might be an important driver for designing the components in the right way. Another thing to do, like I said, is version your services, but also to try and make consumers of those services as tolerant as possible to changes. Because every time that you bump a service API and it's some kind of breaking change, you might have 10 or 20 clients using that service. If you somehow need to update all of them, then changes are still going to ripple throughout your whole application. And pretty soon, well, you have a modular application, but if each change means you need to touch all the other components and update them, it's not really that modular. You just have a big monolithic thing again. It's just broken up into many pieces that are all interconnected. So take care of that. Try to minimize the effect of such changes. And stay flexible. I mean, we're all in this business for some time, I guess, and the only constant is change. Technology change, requirements change, and that means that we need to stay on top of that and deal with that. And finally, we have to design for failure. I mean, our systems are going to fail. We know that. They have been doing that for a long time. So that's something we need to take into account. And that's something we also need to actively deal with and handle in our development, in our testing. It was mentioned earlier today, Chaos Monkey at Netflix just randomly stops nodes in their production infrastructure and actually make sure that their customers don't notice that. So that's something that's important. You should really do that in your own testing environments as well. That totally changes the mindset of developers when you start doing that. Monitoring is also a very important aspect because, well, you first need to notice that something's down, and for that you need to have some form of monitoring in your application, otherwise you'll never know if that happens. Maybe something I didn't even mention here, but that's also becoming more and more important nowadays, is the security aspect of services. That's also something that's usually added as an afterthought in cases. So also keeping that in mind when you start designing your architecture is very important, but that's sort of generic, not specific to microservices. So I hope that gave you a little bit of an overview of what microservices are all about. It might have confused you even more about them. We'll see. At least I have a demo to look at in a little while that hopefully shows some of these things in practice. And, well, since microservices can be in any language, and we at Luminis Technologies use OSGI a lot, I'm actually going to do a demo of how to implement microservices using OSGI. And before I do that, I probably need to give a short introduction of what OSGI is, unless everybody knows it already, but I'll give a short introduction. So OSGI is really a framework that provides you with components, or as they call it, bundles, that can easily be deployed in a container and even updated, added, and removed at runtime without having to restart your whole application. The nice thing about these bundles is that on the one hand, they hide all the implementation details. You can share code that's in the bundle, but by default, nothing is shared. So you have to be really explicit about the things you want to expose to the outside world. And not only do you have to be explicit, you also have to version them and make sure that you have some kind of semantic versioning in place, that when things change, that reflects in a change in the version number. And maybe one of the most important aspects of OSGI is that it provides you with a service registry. So the standard way for different bundles or different components to interact with each other is through services. And by default, the service registry in OSGI is local to the single JVM that's running the OSGI container. So you have lots of really small services. Typical applications that we write have hundreds of components and maybe even thousands of different services. They're all very lightweight and they can come and go dynamically. So this style of development already sets you up for an environment that's way more dynamic and forces you to deal with all the different dynamics that you get when you start scaling stuff out later on. And at the moment, OSGI, at least for Java, is still the most widely used modularity framework. There's Jigsaw coming up in Java 9. That's probably gonna either replace part of OSGI or interoperate with it. We'll have to see how that goes. But a nice thing about OSGI, it's there. It's been under development for more than 10 years, and it runs on any version of Java, from the really small embedded stuff to the big enterprise stuff. So, lots of talk for a developer conference. It's time to slowly ease into showing a little bit of code. And that's the moment that I go in the wrong direction. So I talked about OSGI having bundles, and bundles are really just jar files. And the only thing special about these jar files is that they have some kind of metadata in the bundle manifest. And that metadata tells the OSGI container how to actually run the bundle. So there's some stuff in there that tells you about the name of the bundle. You can specify a version. And well, what's more important for a developer, there's also a way of specifying sort of a starting point, what would normally be your main method in Java. So in OSGI, that's the bundle activator, and it actually contains a start and a stop method. And those are the two methods that are actually invoked when your bundle gets started or stopped by the container. So that's where you start writing your code. I also talked about sharing code. So that's another thing you can do if you have certain packages in your bundle that you might want to share with others. And typical examples are the actual service APIs that you probably want to share with others so you're all talking to the same interface. So you can do that by providing metadata that exports certain packages in the specific version. And the other way around, you can also import packages that have been provided by others and even provide a version range for those. And sort of wiring all of that up is done by the OSGI container. So when you start your bundle, it will try to resolve all those dependencies. If that succeeds, your bundle will start, your start method will be invoked, and you can start doing your stuff. And doing your stuff can, for example, be publishing a service so other bundles can look that up and use it. So that's really OSGI in a nutshell. And there's one more thing I want to mention about that, and that's remoting. Because up till now I've said OSGI has a service registry, but it's local to a single container. That's not very useful in a cluster. You'll probably have multiple processes running on different machines, and you need some kind of way to connect them all. And in the previous talk, we saw that you probably need some kind of discovery mechanism and key value store that's distributed along your cluster to actually make that happen at a low level. And what OSGI actually provides for that is a remote service registry. So with these remote services, you can just say, okay, I have this service here, I want to publish it, and I want to publish it in the whole cluster. It's just a matter of adding a single property to a service, and it will become available in the cluster. Of course, that doesn't happen magically. You need some kind of implementation of this discovery mechanism, and there's actually different kind of providers for that. For local networks, you have stuff like SLP and Bonjour that do discovery on a local network. And for cloud environments, you usually end up either talking to something like etcd or maybe Zookeeper or something like that. So those are implementations that you can use for discovery. And once those services are discovered, they are just usable in the OSGI container as if they were local services. So there's really not much you need to do from a development point of view to transform a locally running application into something that runs in a more distributed way. So the last thing I briefly need to touch on is Amdatu, because we're going to be using a couple of those components in the demo. And Amdatu is actually as we call it, a set of open source components and tools to build modular applications in Java. It's all open source, it's Apache licensed. If you go to amdatu.org, you'll find all the different components there. They're all based on OSGI, and a lot of them are also wrapping existing technologies and allowing them to be used in a modular world. So I have lots of different stuff in there, from web components to schedulers to all kinds of stuff. So it might be interesting for you to take a look at that. And as a development model, well, we're basically adopting a lot of stuff that makes sense nowadays. So it's based on OSGI. We're using B&D tools, which is actually a plugin for Eclipse, and probably soon will also be available for IntelliJ. At least they're working on that at the moment. And that really gives you an environment where you can quickly deploy and run your code. Because it's modular, it makes it more easy to just compile a single module and drop it into an already running local application. So while in Java EE you usually end up using some kind of tool by zero turnaround who keep calling you every week about not using JRebel yet, and they will, well, they'll still call you even if you tell them you're using OSGI and you don't need that. They kind of not remember that, but it's really a way of quickly developing and deploying stuff, not having to wait for a couple of minutes to see everything get compiled and get restarted, etc. So for a developer, it's a really nice workflow. We base all our stuff on Git. We have, at least in the Amdatu project, used the Atlassian tool suite for just about everything we can. And if we look at sort of continuous integration, continuous deployment, depending on the kind of environment that you try to deploy to, we have either a solution based on Apache Ace, and there'll be a session on the Internet of Things after this one that goes into more detail about that. And we also have an Amdatu RTI, which kind of goes back to the previous session about running with Docker containers and Kubernetes and those technologies, and providing a really easy way of deploying stuff to the cloud. And that's all integrated with our build servers, etc. And nowadays, we wouldn't have a nice build if we weren't running Gradle, so that's what we're using as a build tool right now. I'm not going to get into any religious wars about that stuff. Okay, lots of talk. Let's try to demo. I'm just going to turn on mirroring so I can actually see what I'm doing here. And what I have here is an Eclipse project, and you probably cannot read anything on the left very well. Well, you might, it's a pretty big screen, but it's not the most important part. I'll show some code examples, and those will show up in a bigger font. So to demonstrate how to do microservices with OSGI, I set up a fairly simple project, and I thought it would be interesting to do not a Twitter client, because everybody does that, but a weather service, because nobody has provided a good one for that yet, so I might as well give it a shot. So my weather service starts out pretty basic. I have a service. It can predict the temperature in the city. It's a starting point, right? So that's the API that we have. And in terms of microservices, later on we'll split that into a client that's actually using this service and one or more backends that provide it. And just show you a little bit about the implementation, because that's the big trade secret we have here. This is our weather service implementation, and it will predict the weather by first sleeping for a little while, because it's a difficult operation. And then, well, the magic is just the length of the name of the city determines the temperature. It's a demo, so okay. So that's actually our service implementation. And to make that work as an OSGI service, we have an activator here that will publish that weather service. And that's a pretty standard OSGI service. The only thing I added here is one single constant that tells the OSGI container, hey, you can also remote this service and make it available in other containers. At first, we're not even going to use that, but I'm going to put that bit of code in right now so we have it when we need it a little bit later. And of course, we also need a client that will actually invoke the weather service and get some of these temperatures. And that's actually, for this demo, going to be a shell command, because that's easy to just play around with. OSGI comes with a shell, and you can create new commands for it. So we actually create a command, a city, and we can provide it with the name of a city, and it will invoke the weather service and print the result. And we also, and that's probably going to help us a little bit later on, have a command that asks the weather for a whole bunch of cities. Again, that's an OSGI component, so we need a little bit of definition here. And this is a little bit more boilerplate, because to create new shell commands, you actually need to tell the shell what the scope is, which is just a generic name, and then the names of the individual commands, and those map to the different method names that we just saw. Publish that as a service. Actually create a dependency on the weather service, because we're using that in our commands, so it needs to be injected, and by defining it like this, it will automatically be injected, and that's about it. So this is the code, and like I said, I can package that up in different bundles in OSGI to make really small modules out of that. And for example, we have one definition for a model here that just packages the weather service API. So this is a really small bundle. It shares the API and actually exports that so it's available for others. I have another one that has the client, and that just has the client package inside its bundle and the definition of the activator to get the client started. And the third bundle we have is the actual implementation of the weather service, and that just contains the implementation package and again an activator which will then publish the service. So how do I combine that into something that I can run? I need a run definition for that, and a run definition basically just tells me what bundles should I group together into one executable. And for that, we have BND run files, and these are also not very magic. I mean, there's nice Eclipse editors for them that sort of makes it a little bit easier to edit, but in the end, this is the definition that comes out. It basically tells Java to run an OSGI framework on Java 8. It has some definitions on where to keep a cache. It has some logging parameters, so we can get some logging going. And here's just a simple list of all the different bundles that we're going to run as part of this application. So I can either run this in Eclipse and debug it, but a little bit later I'm going to run multiple instances, so I'm going to switch to a shell and sort of run everything there. And hopefully that's sort of readable as well. It's a little bit high. First, I need to run the Gradle build and actually generate the executables that I had defined in the BND run files. And as you can see, most of the stuff was already up to date because I sort of prepared the demo, so it's not really recompiling everything. But now that I have everything running, let's first start by running our whole application in a single jar file. So I just started with java -jar, and this is a jar that just came out of the build. It starts up, it shows me the prompt for the OSGI shell, and what I usually start out with is just typing help. I have no clue what I want to do. It gives me a list of commands, and there's one command to say city, and let's check the temperature here. And it actually takes 2 seconds, because that's programmed, and it returns the temperature. So this is just running as a single executable, nothing microservices about that. But let's split up our example into different parts and see how that works. And I'll briefly first go back to Eclipse to show you how that is defined. And what I'm basically doing is taking the same set of bundles that I had, but I'm splitting them up. So I'll create one run definition for the client, and that will only contain the client bundle and the API. And to actually get remote services running, there's a couple of extra bundles that I need to add to actually make that work, which are these 3 Amdatu bundles, which actually provide the implementation for that. And since by default remote services use a sort of REST-like calling style, we also need a web server, which is provided by Jetty, and that's also just a bundle that we can deploy into our container. So this is our client. It contains the client and the API. I have a similar one for the server, and well, you can sort of guess it contains the implementation and the API, but not the client. So let's run this example and see what happens. So I'll start with the client. That's running here. You see a little bit of debug output coming from the web server, but you're free to ignore that. And I can already try asking for the temperature, and I'm getting back 0. And that's because there's no implementation available, and by default it just returns 0 degrees for that. It's probably not what you want to do in real life, but hey, it's a demo, so I took a few shortcuts. So let's now start a backend and see if we can actually get some temperature readings. -jar, and I'll run the backend. That also starts up, and I can actually, with the shell, also just list all the different bundles. You'll see the weather implementation here. And just to show you, here's only the client and the API. And let's try again. And what you actually see now is that the call is done to the other process. It's calculating the temperature there, and the result is being passed on to the client again. So that's a really simple first step. Now let's make our system a little bit more highly available, because I said, well, we could start, for example, multiple backends. Let's do that. Starting a second one. That started as well. I can still ask for, and I'm not that creative in city names, so I'll just go with ABC. That's working. B, okay, that's all working. And as you can see, it's always invoking the first container that we started. And that's really because in OSGI, I just created a service dependency on any weather service. And the OSGI spec says that if there's multiple services available and there's nothing else to distinguish them by, it will just take the oldest one. So the one that was available first will always be used. And just to demonstrate that, I can also stop this one, go back to my client, and see what happens. And of course, it's a demo, so something should have failed. There you go. I was a little bit too quick to discovery. It takes a couple of seconds to see that something goes missing. So it actually thought that the first container was still there, tried to invoke it, and I got a runtime exception. And that's actually something in a non-demo application that you should always handle exceptions. Because whenever you're invoking a service, it could be going away at the moment you're invoking it. So you always should be prepared to deal with some kind of exception and either communicate that to the user, as I just did in this example, or maybe retry and see if you can make it work or something like that. So I can restart this one again, and well, you can see it's probably still going to this container because now it's the oldest one around. I stopped the other one, so it doesn't count, it restarts. But it doesn't really give us some nice features yet regarding load balancing and high availability. So let's see if we can make that work as well. I'm briefly going to go back to my Eclipse. And there we're going to see how we can implement a simple load balancer for this scenario. So in our client, we really have a situation now where we can have multiple weather services available. So what we could do is implement some kind of round-robin load balancer that just collects all these services that are available and invokes them one at a time, going through the list and then starting at the top again. And I can do that in OSGI quite easily. I'll show you what that looks like. This is my load balancer. It needs to do a couple of things. It has two methods to add and remove weather services as they are automatically discovered. And when they're discovered, this method will be called. So I can keep a list of them. And then whenever I want to predict the temperature, I'm going to go through my list. At most, I'm going to try 5 times and try to just invoke the first service. I'll keep an index that I can increase and go back to 0 once I'm at the end of the list. And in the end, I'll invoke the predict temperature of the remote service. And what I'm actually doing is publishing myself as a weather service as well. And if I do that with a service ranking property in OSGI, I can make sure that any client running here will always first go to the highest ranked service. So if I create a load balancer with a ranking of 100, for example, and that's actually happening here. Here I have my service ranking. Then I can make sure that any client will first find this one, and if it's because it's the highest ranked one, that's the one it will be using. And I can collect in my load balancer all the other services and just reroute the traffic to one of them. And I need to obviously make sure that in the load balancer I'm not finding myself, because that would create an interesting loop. So there's a little trick that I use, because all the other services will always be imported because they're remote services. So I'm telling the load balancer only look for services that are somehow remotely published to our container. So you couldn't, in this demo, actually run a local weather service as well and make that work. I would have had to tweak the filters a little bit for that. So let's see how that works. That's the wrong one. That's better. So my client is still running. And I need to stop that because the load balancer is actually part of the client. So let's try to start this one. And I'll list the bundles again. You'll see it still contains the weather client, the API, and also here the load balancer that we have, which will reroute the traffic. So let's see if that actually works. Okay, that's going to the first one. Now it goes to the other one, round robin, and if I do a third one, it goes to the first one again. So this is where my other command comes in. It saves me some typing. It will ask for about 26 different cities, and you see it nicely alternates between the two implementations. And if I'm really quick, and I'm probably already a bit too late, I can also start another one. Yeah, it's not yet picking up. I'll repeat the command in a little while. See, now it's using 3 different backends. And I can actually also simulate a somewhat faster backend that doesn't need to calculate for 2 whole seconds. Let's do that as well. I have a delay system property in there that I can make it 100 milliseconds. And I can run this one. And that's going to be a little bit faster. Let's see, might have to wait a couple of seconds before it becomes active. Let's see if that works out or not. Yep, you see it actually uses this one as well. The only downside, it's a very simple round robin, so even though one of the servers is a lot faster than the other ones, it isn't being utilized anymore. So you're not getting the full advantage of the speed up of a faster server. In order to do that, we could start actually measuring the response time of each remote service, and then modifying our load balancer to take that into account to always favor machines that are faster than slower ones. So let's do that, and let's do that in 2 different steps, and first try to come up with some kind of average for the invocation time for each service. And for that, I created a very simple OSGI service called Quality of Service. And it will publish a Quality of Service for every service it finds. It will give it a name and some kind of unique ID. And you can ask the average invocation time, and based on that, a weight that you can use in a load balancer. And the implementation of that is somewhat like this. So it's also sort of a proxy that sits in front of a normal weather service. So when you actually invoke the weather service, you go through this one as well. And you will go, well, it actually measures the time it takes to do the remote method call. And then it increases the number of invocations, and it adds it to the total time it took. And then it can then later calculate the average time based on that. So not really rocket science, just some bookkeeping to keep track of how fast a service is. And I actually also created a shell command so I can look at these averages. So let's have a go at showing that. That's my new client. And probably if I try it right now, I'm a little bit too quick. It hasn't discovered the other services yet, so I need to talk a little bit more and try again. And there it goes. And you see it's invoking all the others again. And it's actually calculating how much time it spent in each method call. And I can actually use the average command to get some kind of feedback on that. But what I didn't yet do is make the load balancer actually take that into account and use this information. So I'm going to stop this client again and quickly go back to my second implementation of my load balancer, which is a little bit more advanced as the one I showed before. It will actually randomly pick a weather service, but it will take into account the response time, favoring ones that are quicker over ones that are slower. So, well, there's a little bit of math here, not something really to go into detail about, but let's see how that works. So we have a new client, and again, probably take a little while before all the other services show up. Show the averages again. I don't see anything either. Just wait a couple of seconds. Sort of increases the suspense, right? there they are. Now let's invoke them. And almost immediately we see it favors the faster one. I can run it a couple of times. And actually in this example, the faster one is so fast that it should really always go there and not even bother invoking the slower ones, but hey, they're still around though. They get some traffic still. And it's good because if it actually, the fast one stops running, already a little bit too slow, it will still continue and invoke the other ones. And I'll restart it again. I can still see my averages, and I just stopped the fast one. So this is a nice way of creating a load balancer that will actually measure how fast services respond and distribute the load based on that. I have one final example. I still probably have a little bit of time for that. Yep. Which is health checks, which are another important thing to look at when you're writing these distributed systems. And I created a very simple API for that as well. I have a node interface, and each node gets some kind of unique name, and it has a health check method that will actually check if the node's still healthy using a very simple algorithm. I actually use an MBean in this implementation to look at the system load, and if it becomes too high, I'm just going to say it's not healthy. It's always a little bit tricky whether my load will actually be high or low at the moment, so we'll see what happens. And that's something that's actually implemented both in the client and in the backend, so I need to restart all my different nodes. I'll have the client running. I'll stop all my backends. And I'll start a few of them again. I'll just stick to 2. That's probably good enough. And I should have some new shell commands here as well. Yeah, it's a little bit hidden here. And this is my health check. And apparently at the moment my system load is pretty low. Well, not doing any background computation at the moment, so that's not really that surprising. If I were to ray trace some stuff or whatever, probably get the load up, and you would see the nodes becoming unhealthy. And that could also be something that you then tie in again with the load balancer. But for the demo, I'll leave it at that. Just want to mention that all the code that I used in this demo is available on Bitbucket, and I'll have a link a little bit later. So let's go back to wrap it up. Go back to the slides. So wrapping things up, I sort of gave a short introduction to modularity, to microservices, introduced OSGI and Amdatu, and show you how to build a modular application using OSGI and based on a microservices principle. And if you looked at the example, then you probably see that it's quite an interesting mix to use OSGI with microservices, because the OSGI modules are even smaller, and by themselves they could never be one single microservice. So within a microservice, that gives you some modularity to build your application not as a single thing, but in a more modular way, and still hook everything up through microservices, maybe even integrate it with code running in different languages. And what I haven't shown in the demo, that you can also easily publish REST APIs like this and also invoke them. So it's not just remote services, but you can also use REST endpoints for that. So there's lots of opportunities there to make that work. And hopefully I've shown with the demo that it's not really that hard to get a cluster up and running and dynamically discover services like that. And obviously this is just a small demo, but you can probably see how that would scale up. So to conclude, I have a few links. about the stuff I talked about and maybe talked about not so much, such as Amdatu. The demo code is down there. I obviously need to plug Paul's book a little bit if you haven't read it. The B&D tools plugin is available there. So if you want to see any of that, just look it up or watch the video afterwards, because this stuff is all recorded, so probably can watch it back there as well. And probably have 1 or 2 minutes left for questions. I want to thank you for your attention. Any questions? You all want to have dinner. I'm just going to, one question, yeah. I'll first repeat the question. So the question was, not all Java libraries at the moment are OSGI compatible. Especially a lot of the new stuff usually isn't yet. How to deal with that? So on the one hand, that's exactly why we started the Amdatu project, to make OSGI compatible versions of existing technology. We're not trying to reinvent the wheel, just reuse what's there. We also always talk to the developer community of such a library and see if they are willing to provide the extra metadata to make such a component OSGI compatible. After all, they know the most about this component, so usually they have a pretty good idea how to make it OSGI compatible. In practice, they don't always know about OSGI, so it doesn't always work out. Well, that's the options we have. Engage with the community, try and see if we can either provide a patch for it or if they can maintain that. If not, then you have to maintain something like that yourself. And yeah, that's why we try to provide as much of that stuff in the Amdatu project, so you don't have to go looking for it all over the internet. But we're definitely not the only ones making OSGI compatible components. Very last question, I think. Yeah.
So how do you deal with services not running on Java or the JVM at all?
So you have two options. You can go back to the standard REST services and use those. And by just using a normal Java REST client, that's pretty easy to integrate. And another option that you have is if you integrate those services into the OSGI remote services specification, which doesn't require all services to be implemented in Java. For example, within Apache, we've been donating to the Apache Eclipse Project, which is actually a C implementation of OSGI. So there's a few differences in between C because it's not even object-oriented, but you can create APIs there as well. And for that, we actually have a bridge to also talk to remote services, so that way we can integrate C and Java, and you could do the same for other languages. Yeah. Very, very last question, Tara.
Are you implying that every client's load balancer and quality service has to basically provide implementation of the load balancer?
Yeah, so the question was, do you have to actually provide a load balancer for each individual service? Because that's how it was done in the demo. I had a load balancer that actually implemented weather service. So it's not very generic, right? So in practice, you would probably not do it like that, but use something like a dynamic proxy in Java. So you could implement any API and just intercept all the calls and reroute them. So that would probably be the implementation to use in a non-demo setup, but slightly more complicated and not as readable. So I didn't do that on purpose here. Yeah. Okay, I think it's dinner time. Thank you.